Hi, everybody. Hey, Anna.
Hi.
Today I don't have Jessie with me. She's behind the screen. And so I've got Anna.
Pleasure to be here.
Cool. Okay, so let's go because we have a very interesting program for today. And today is the last edition of our DS meetup for this year. We have a very inspiring session and amazing speaker. The first two speakers, we have Moshtaba Farmban and Boyang Zhao. Let me tell you something about them. Boyang is a senior data scientist at One-to-One Analytics ING, and he received his doctorate in computational and system biology and bachelor's in biomedical engineering. He has worked extensively with data science in multiple domains, including in preclinical R&D and clinical studies in academia and pharmaceutical industry. With his own company and in the healthcare sector and in the hedge fund. Whereas Mostabar is a senior data scientist at People Analytics ING, and he holds a PhD in computational physics. He has been also involved in different data science projects using NLP technique, recommender systems, and knowledge graphs and causal inferences. So the presentation is about semantic search with domain-specific and embedding models in production monitoring in fintech. Guys, the floor is yours.
Hello all, thanks Sam and Anna for the introduction. Today, together with my colleague Bo Yang, we will be presenting one of our recent work, which is about the semantic search and how we monitor it in production. Bo, if you go to next slide. Yeah, we have been already introduced. I just want to say that this presentation is based upon our recent paper published in Calling 2020. And I'm going to thank Nikki von Ommeren, one of our collaborators in this work. So in this presentation, we will be covering following topics, actually. I'm going to explain how we started this journey and how we came up with the search engine, what is how our text mining pipeline working, how we expand a search query, how we take care of ranking of our retrieved documents, and at the end, how we monitor our language models in production. So as you know, ING as one of the financial institute is often being asked by authorities how many issues we have registered related to certain topics. You can think of money laundering, data leakage, and so on. And it's going to be a tough and tedious task for our risk officer to create and make a very complete report because of the following challenges. In our financial data, we use a lot of jargons and abbreviations, and issues will be in different languages. And sometimes issues are contextually related to a search term, but they don't have that search term exactly. For instance, if you think of data leakage, there are a lot of issues related to data leakage, but they don't have data leakage as such. And one more thing, after gathering all those documents, they have to spend quite a time to fix false negative and false positive. Therefore, we stepped in to solve this problem, and that's how we came up with a search engine, which automatically suggests relevant keywords to our risk officer, where they can search among them, select among them, and search through all those documents. This search engine contains of three main components. First component is text mining pipeline. The second one is that our word embedding, which we generate similar words from that. And the last one is that how we rank our retrieved documents in terms of relevancy. I will be focusing mainly on part one and partially part two, and Bo Yang will be covering the rest of the presentation. So how our text mining pipeline works. So as you see, it contains of several stages. At first stage, we detect the languages, And our current search engine support the 3 languages. It can be easily scaled up to different languages, either by creating a separate pipeline or translating them to English by using some offline translators. The second is that tokenization. What does it mean? It means that we're gonna break long sentences or any sentences into a smaller unit. And you can think of this smaller unit as a word. Basically, one sentence, we break it down into words. And after that, we label them. And first, label them like labeling based on name entities. You can think of one token can be organization, can be location, a person name. Then we're going to lematize them. So plural nouns will be converted to singular nouns, and different forms of verbs will be converted to base form. Then we're going to label stop words like this, of, are, or are. These sort of things will be labeled as a stop words. After that, we're going to do data anonymization, which is essential in our financial data. We have to anonymize our data if there is a person's name or credit card number and so on. We're going to do that using regular expression and name entity recognition. After that, we're going to do abbreviation detection. We're going to make our text unified. We don't like to have at the same time a full form and also abbreviated one. We're going to detect them, either keep full form or abbreviated one, because in our further analysis, it will make some noises. Then afterward, we're going to remove stop words. We have already tagged them and labeled them. We're going to get rid of them because they're not going to add any values in our analysis. After that, we do engram detection. We want, for instance, a word like New York will be counted as a one unit and one token. We don't want to have 2 tokens like New and York. So that's why we do engram detection. For instance, you can think of financial market. We're gonna count financial market as a one unit, not 2 separated tokens. Then we have a word embedding. Why do we need word embedding? As I discussed before, we're gonna expand our search query to similar words. So how we are going to do that? We're gonna use a word embedding. Word embedding here is a shallow neural network where as an input, we have our text data, and output is a vector space. In this vector space, all the tokens and words are mapped into this vector space. And words which are semantically related to each other, they are much closer to each other. So if you think of a privacy in this figure on top right on top, we're going to look at the privacy and what are the words around or close to privacy. Then we're going to count those words as similar words. We have trained our model on 160K financial data. But the question is that how good is your word embedding? How good is your similar words? We're going to do 2 different evaluation. One is that intrinsic evaluation, which is simply here is a human judgment. If you think of one term like privacy, we're gonna see what would be similar word to privacy in a pre-trained models like Word2Vec, which is trained on Google News, Glove, which is trained on Wikipedia, and our Word2Vec model, which is trained on our domain-specific data. As you can see that the word generated from our domain-specific is more relevant to our banking domain and a financial domain. By the way, those numerical values in the parentheses shows our similarity score. 0 means that they are dissimilar, and 1 means that they are identical. Another way of evaluating your word embedding, our word embedding, was basically applying this word embedding for downstream tasks, like for a classification perspective. So here we use our embedding layer followed by GRU architecture, and we realize that our custom word embedding only trained on 160K documents perform as good as pre-trained one, which trained on millions and billions of records. Then here I will pass it to my colleague Boyan.
Great, thank you much, Daba. So this current aspect right now is about term set expansion, but I just want to also bring us back a bit into thinking about this is in the context of information retrieval systems, right? And if you think about the information, this IR system, there are actually two dimensions that I want to mention. One is about sensitivity, the other is about specificity. So far with the similar word expansions, what we are trying to tackle is really about trying to minimizing false negatives, which is focusing on sensitivity. So we want to expand this user queries to bring in more queries terms to encompass a larger scope so that we can get as much of the relevant documents back as possible. The other dimension is about then specificity, and we try to tackle this using relevance ranking. So imagine you have now all the returning documents, but not 100% of them are perhaps relevant to the query. So we want to rank the returning documents so that the most relevant documents appear on the top of the list. And so this is the last part that I'm going to talk about, which is relevance ranking. If you talk about this particular topic, what we're really addressing then is about semantic textual similarity, or STS. And to put it into layman terms, that all that really just means we want to compare the queries against a list of documents, right? And just to give you a bit more of the mechanics behind this, it's really rather simple, right? So you can have a list of documents and the queries. The first step in this process of comparing documents and queries is we want to do an encoding step so that we can turn all the textual information into mathematical representation that machines can understand. And in this particular example, the numbers don't matter except to say that now we can turn a mathematical representation of all the text. The next step is to calculate the similarities among them. So what is the similarity between this query corresponding to this document and amongst the other documents as well? Once we have the similarity scores, then we can rank merely just based on those scores. And the higher the similarity score, the higher the ranking, and perhaps the more relevant those documents are against the query. So I'm going to show you a bit deeper in the next two slides that kind of cover a bit more of these two aspects. The next two slides is going to look a bit busy, but I do have a very clear and concrete message for each of them. And that is just really about, for example, the encoding step. You can really categorize down into broadly two categories, which is related to non-embedding based methods or embedding based methods. And this can ranges from very simple techniques such as the TF-IDF models, which are merely based on the term frequencies within the documents, to more sophisticated approaches that's based on neural networks. Really, the only message I want you to take away from this slide is that there is a whole bunch of different methods to address the problem of semantic textual similarity. And the ones that are shown in bold indicate that we have actually tried out a whole bunch of them in our work. Just to go one step deeper into the neural networks, this is another busy slide, but again, the message really here is to highlight that these neural network-based models also have a very diverse set of underlying architectures and the different methods or tasks that are required to train them. And this ranges, for example, where they will ask the model to mask a certain word and ask the model to predict the masked word, or they can ask the model to ask whether this particular sentence is the right sentence following the previous sentence. One last example perhaps is question and answer, whether the list of questions, if a given answer is the most appropriate for a given question. So the diversity of the architectures and the diversity of the training tasks also differentiate in part the differences that we see in these neural network models. And this can have potential implications when we look at performance in the next couple slides. So with this in mind, the first thing we want to do is using this diversity of different models to first evaluate the time performance. So as an experiment, we actually timed how long it would take for a variety of different algorithms to encode about 30,000 records. You can see here, for example, the very simple algorithms such as the TF-IDF is essentially almost instantaneous in terms of their encoding time. But what is most striking is that if you look at the BERT models or BERT-based models, you see that the time performance is actually rather really slow. And in one instance, it can take up to 7 hours to merely encode only 30,000 documents. So just keep this in mind, and these things can become really time prohibitive when you're thinking about trying to build productionized models that have to run at a much greater speed. So this is even independent of how well they will perform in terms of their ranking capabilities. So time performance aside, the next thing that we can then focus on is just exactly that. What is the ranking capabilities of these algorithms? So before I introduce our results, I do need to spend just one slide on introducing what is the metric that we can use to measure the performance. And this is that slide showing here, which is precision at K and also the average precision. So I just want to bring to your attention the bottom half of the slide, which is this graphic here. On the x-axis is basically indicating the number of documents you're returning. The y-axis represents the proportion of documents returned that are the most relevant. So the way that you read this plot, for example, is if you're returning one document, the question is whether that document is relevant or not relevant. If it is, that means 100% of that document is relevant. Otherwise, it's 0. And if you say returning now 2 documents, you can ask the same question. If both documents are relevant, they will have 100% precision. If only one of them are, that will be about 50% and 0. So you can repeat this procedure, so on and so forth. In this particular example, go up to 175 documents. The only thing you have to keep in mind in this particular evaluation is that the higher the curve, the better the ranking. So the red curve here indicates it's a very good ranking algorithm compared to something that's in blue here. Now, we can also turn this graphical representation of the assessment into a single number. And I won't go into the mathematics here, except to say that we can also look at the average precision to evaluate whether one algorithm is better than the other. So the higher the average precision, the better the ranking. So now on with the results. So we manually annotated the topics of hundreds of documents and assessed the ranking algorithms across a broad set of different classes. So there are a couple key points I want to highlight. The first is that if you look at the very simple algorithms, such as the TF-IDFs or even our domain-specific word embeddings, you see that they were actually performing rather poorly. And the reason for that is, even though they were good at picking out certain words and relative to their frequencies, they weren't very good at understanding context. So in this particular example, we're asking the algorithm to picking out, for example, documents related to statistical models. And there are, however, other documents that mention the word model in other contexts. There are models that's related to the business model, related to the model number of a device, such as a mobile phone or ATM, that has no really the same context as a mathematical or statistical model that we're trying to find. And these models fail really bad in those very context-dependent queries. And then you can also see that for BERT models, they do actually improve the performance. But keep in mind, they are actually very time-intensive, and they're rather takes a very long time. Then if you look at these universal sentence encoders and different variants of them, these are created by Google, you can see that actually outcompete the BERT models. In addition, there's also different variations among them. So a couple slides earlier, I told you about there are many different underlying architectures and different training tasks and different input data that's used to build these models. And these different versions reflect those differences. So the different performances that you're observing here is in part indicative of those variations that's underlying that. So all in all, from this particular set of evaluations with many different kind of queries, we eventually decided on using the multilingual universal sentence encoder, which has a fairly good performance and is also capable of processing multiple different languages. So the next question then we asked is, can we do even better? So I won't have time to go into the details of this slide, except to say that we did try to actually use an additional Siamese architecture to fine-tune on the Muse models on the GPUs with a particular next sentence prediction tasks. If you don't understand what I said just now, it doesn't really, it's not the most important thing, except to say that we did try to fine-tune our models but the performance was actually still comparable to that of the pre-trained models. So we did not dive deeper into fine-tuning further in that case. So putting all these together, we have shown you so far that we have built an entire end-to-end semantic search system where we have an underlying text mining pipeline to pre-process everything. We have a word embedding system for term set expansion, and also a sentence-based model for ranking. There are two additional points I want to point out. One is that in terms of the implementation for the ranking, we actually also use the package FICE that was created by Facebook, which really enables a high volume real-time similarity calculations and the indexing in memory of the documents. And this is basically can be then used app production in real time. The other comment is that in order to stay relevant with our word embeddings to suggest the most relevant similar terms, we actually continuously train our word embedding models with new, fresh data. However, because of this approach, this also brings in another issue, is that if we're going to keep on training our models, we have to make sure that the newly trained word embeddings do not degrade the performance. So in this case, it's challenging because we're not simply building a machine learning model where we can just measure its accuracy or the AUCs. Here, we're building models where we have to understand the interrelationships among the words and make sure those interrelationships don't change. So we have to develop additional novel techniques in order to measure the stability of our word embeddings. And that's what I'm going to talk about in the next couple of slides. So in order to measure the stability of word embeddings, we first need to understand what is the baseline variability from run to run on the same data. And that's exactly what you're seeing here on the left, is we built two independent word-to-vec models from different runs, but on the same data. Each data point here represents a pair of words with their cosine similarity values based on either the first run of building the model or the second run, right? And this spread, effectively, then what you're seeing is the intrinsic variability that you can observe with the data. Now, in order to have a positive control, we ask the question, can we bring another model that's very drastically different? And does that change the behavior that we're seeing in this visualization? And that's indeed what we did. So now we're comparing the same custom trained model, but now compared against a word-to-vec model that was trained on Google News. So a completely different input data set, right? And you can see this very vast difference in terms of their relationships. So knowing this, we wondered then if we can have a way to quantify these differences, effectively what we can do then is monitoring the intra-relationships among the word embeddings themselves between old and new models. So what we can do effectively is we can bootstrap this baseline to generate node distributions and measure how much deviation from distributions that's generated based on new models. So I'm going to animate what I just said in the next couple of slides. And that effectively is the following, right? This is the same plot that we showed you earlier where we sampled m different words and compared between different runs, which give us a baseline. But instead of just doing it once, we can actually bootstrap to sample many, many different times. And also then we can do a quadrant to look at different slices of the similarity quadrants. And for each quadrant, we can generate a distribution of the correlations among them. The details of this, I won't have too much time to go into detail, except to say that essentially what we have done here is to convert via bootstrap method to generate a underlying node distribution that we can use to compare against. Right. So what that would entail then is by comparing the distribution from models that was done run to run on the same data, we can generate the underlying node distribution. And if we now also repeat the same procedure, but looking at what is the distribution between an old versus new model, then we can generate a distribution for the test distribution. And then we can ask the question, can we then measure that distances, right? And this is essentially the plot, I think that's the most clear in the end, that you can also see the differences. So the underlying gray is the node distribution that we can observe that provides the baseline variabilities that we observe. And you can compare this in contrast with different set of models. So if we're comparing a new versus new model training on slightly different input data sets, you can see that the distributional shifts are rather small. However, if you're comparing this against a model that's based on, say, the Google News input data, you can see a very vastly different distribution. And we can quantify this using the Jensen-Shannon divergence, and you can also quantitatively see these differences. So by defining a threshold, then we can use this as a way to monitor any particular intrinsic drifts that we observe in our word embeddings. And this is now being used on production for monitoring procedures. So to conclude, what I've shown you guys in this 30 minutes is the following, is that we have presented an end-to-end semantic information retrieval system that's currently used for risk management. There are three aspects that we highlighted. One is using term set similarity to address the issue of sensitivity or false negatives by using domain-specific word embeddings. We used relevance ranking algorithms to address specificity, and this is related to false positives. And this is done via a pre-trained multilingual universal sentence encoders. Because we're continuously training the word embedding models, we've also presented to you guys a novel statistical approach we're using to monitor continuously the trained models that's currently on production. And this is done via a bootstrap sampling approach of the node distributions, and with the distances of the distributions measured based on a Jensen-Shannon divergence. All the work that we have shown you guys today have also been published recently. So we actually also attended the cooling conference last week. And this particular work is also published in the proceedings as well. So with that, I would just like to highlight all the folks that was involved in this work. So this is the core team, but we also have additional engineers who have also helped us along with this journey. Mushtaba is from People Analytics. Me and Nikki are from One-to-One Analytics. And this was a really wonderful collaboration that came together to build this entire system with lots of moving parts together. So with that, then we would be open for now questions. Thank you so much for listening.
Thank you, Boyang and Mojtaba, for the amazing presentation on semantic search with domain-specific embedded models and production monitoring in fintech. I'm sorry for the beginning. There was quite of noise, a lot of noise. I've got new headset, so hopefully we can make it. And we have a lot of questions. So if you are ready, somebody was already asking about the link of your presentation. If you could share it, Boyang, maybe, to your publication.
Yes, so I think this will be, so if you have the QR code here, you can scan it. And I think if you pause the YouTube later on and go back to this,
Great.
You can take this, and this links to the publication. It has all the information.
Excellent. So we go immediately to the first question. It's how token assignment is done. For example, a name Alex should be under the entity person.
Mashtaba, perhaps that's about token.
Yes, indeed. That's how it has been done, actually. In principle, name Alex has to be recognized as a name person.
Okay, and then somebody else is asking, I think, maybe the same questions about entity recognition to extract interesting data.
Interesting data, to be honest, I'm not sure what does it mean, interesting data, but I mean, you can do to kind of make some insight from your text data, because you can extract some location, organization, name of person, date, and also money. You can use it for some getting some insight from your text data, but interesting data, I'm not entirely sure what does it mean.
You can also check it on the chat and maybe respond better to him afterwards. Last questions, because we've got 2 minutes left. We have, how do you ensure the queries of answers share the same embedding space?
The queries and the questions. So we use the same embedding. So if the question is about whether they're aligned or not, I think that's in part if we are using the sentence embeddings to encode both the queries as well as the documents. So if we're looking at these similarities, if they're similar, they are by that definition close together in the same embedding space, if that's the question.
And the last questions we have is how the word Alex is labeled with person entity.
I think it's a pre-trained model behind this algorithm. So, I mean, there is a model trained that, okay, if there is a token coming maybe at the capital format, starting with capital or being at some specific part of a sentence, it can be potentially a name, actually. So this model trained on number of data and amount of data, then there you can use it for any data as well.
Great. I see that Kedem has added the link to this paper. So thank you so much for doing that. And thank you guys for this amazing presentation. Also want to thank Nikki that she was in your team and she was also one of our star speaker in one of the old presentation of the online data meetup. Okay. Thank you guys. And we go to the next presenter.
Yes, thank you Mochba and Boyoung for your presentation. And now I will introduce you all to our second talk of this meetup. Unfortunately, one of our speakers, Stan, could not be here today. However, Fritz Hermans will talk to you and will present to you. So let me tell you something about Fritz. First of all, he's a data scientist at Financial Crime Analytics at ING. He has a master's degree in physics, and he joined ING in 2009 as a risk trainee. Fritz had various modeling positions across the bank actually, but lately he focused on money laundering detection models. In his free time, he enjoys regatta sailing and windsurfing, quite fun. And today he will talk to you about entity deduplication at scale. So I will give the floor to Fritz and good luck.
Colleague Stan Leijsink is not able to join, so I have to do it on my own, which is no problem. Before we jump into the entity deduplication, I would first like to sketch the context. So we as banks do not only have the obligation, the legal obligation to monitor transactions of our own clients, but we also are required to monitor transactions that pass by our bank. We as a large bank have connections with many banks in the world, and the smaller banks do not have these connections. So they basically use the larger banks like ING to perform international transfers. So these transactions are transactions mostly from people that are not clients or companies that are not clients of ING. So it's a hard task to do monitoring of these transactions because you don't have much more information than only the transaction details. And that's where the deduplication enters. So all the transactions from the same company need to be combined in order to create features for a model to detect potential risky companies. And the challenge is which transactions belong actually to the same company. Companies can have different banks, different bank account numbers, but most importantly, the company names and the addresses can have different notations. So a simple drop duplicates would not work. And this is called deduplication. So the challenge is to identify a single real world entity from multiple different notations. And to show you how challenging this task is, let me show you the results if you type ING in the Dutch Chamber of Commerce website. These are on the right of the screen, you see the first results that you get. So first you get ING Bank, then ING Group. Then there are a couple of, I think self-employed people who are engineers. ING is also the abbreviation of engineer in Dutch. And then somewhere at the end, you see ING Bank again, which is us. So here you see that it's not super trivial to just do a Control F on ING, so to say. There are two difficulties in deduplication. First of all, how do you compare strings? And the second problem is the n-squared problem. Let me explain them both. So there are many string similarity metrics. The most famous one is the Levenshtein ratio, But basically, all these metrics calculate differences or similarities, as you like, based on the number of character edits that you need to make to convert one string into the other. Let's go back at the example from the previous slide. So here you see two instances from the Dutch Chamber of Commerce. One is ING Bank N.V., our company, and the other is ING A Klein BV. And let's take the most famous string similarity metric, which is the Levenshtein ratio for both. So you see that ING A Klein BV and ING Bank NV have a Levenshtein ratio of 0.625. Whereas ING and ING Bank NV, which is basically the same real-world entity, have a lower Levenshtein ratio. That means that this ratio gives a lower number, so less similarity for two strings that are actually belonging to the same company. So the main message here is that there is no single string similarity metric where you can set a threshold and say above this threshold, two company names are the same, and below they are different companies. So that's the first problem. The second problem is the n-squared problem. If you would naively compare all the combinations of strings that you have in your data set, the computational burden blows up very quickly. Especially when you work in a bank like we do, we have many transactions. And if you would compare them all individually or pairwise, that number would blow up and it would not be possible to calculate. The dedupe Python package basically solves these two problems. Dedupe is a package that's open sourced by Datamate, a US-based company, and you can just pip install it in Python. From a user perspective, it works as follows. You provide a data set, you choose the columns that you want to use for deduplication, you choose the string similarity metrics that you want to use, and then you enter into an online learning session where you manually label pairs as a match or as not a match. And then dedupe is trained and it generates deduplication results, basically indicating which company representations belong to the same real-world entity and which others as well. Let me now explain what happens under the hood of dedupe. So the first thing that dedupe does, it applies blocking rules. So there is a list of, I think, more than 50 blocking rules, and these rules are the same first word, the same first three characters, the same integers. And those blocking rules are applied to all the strings that are in the data. And then the smallest set of blocking rules that obeys this manually labeling from the previous slide, that is kept. And for this, for determining this set of blocking rules, a greedy set cover algorithm is used, a branch and bound algorithm. We don't go deeper into that. The advantage of applying these blocking rules is that you only compare strings that belong to the same blocks. So here on the right, you see some basically fake data that I created myself. It's just the Eurostoxx 50 companies, and then different ways of representing their names and their combined with their addresses. If you would naively compare them all, you would have to do this for all the orange blocks. If you apply blocking rules, so let's say you only compare the ones that have the same first word, then you see the number of comparisons that need to be made is much smaller. So this blocking solves the n-squared problem. The other problem was about scoring, about how to determine what the similarity is between the two strings. As I said, dedupe allows you to provide the string similarity metrics that you want to use in your deduplication process. The package is shipped with two string similarity metrics, the normalized defined gap distance and the conditional random field distance. And we have used both. Moreover, we added two string similarity metrics that work on a token level instead of on a character level. And these are the token set ratio and the token sort ratio, which are implemented in the famous Python package called fuzzy-wuzzy. Then these four string similarity metrics are calculated for each pair of strings in the blocks. And these enter into a simple logistic regression model. So let's have a look on the right side of this slide. So we have two pairs of strings, ING Bank NV, and ING Bank and UBS. There we have the 4 string similarity metrics, the affine cap distance, the conditional random field distance, the token set ratio, and the token sort ratio. These are just 4 numbers, and those 4 numbers are the features for this logistic regression model, which would give a high score, a high probability of being the same company to the pair ING Bank, NV, and it would give a low score for ING Bank and UBS. So far, not too exciting, but this is where the magic happens in the DGU package, and I think it's really smart what they made. So what they do is you now have for each pair of strings, you have a probability from the logistic regression model. In the DGU package, a big graph is made where the edges between the nodes are the probabilities from the logistic regression model. The nodes are the entities or the representations of entities that you want to deduplicate. And the first thing that is applied is that there is a connected components algorithm is applied, which is basically an algorithm that splits the whole graph. You should see this as one graph. It would split it into subgraphs that are not connected to other parts of the graph. So in this case, we would have component 1. These are the things with Banco in the name. And a component 2 would be the cases here with Airbus in the name. Then for each component, hierarchical clustering is applied to the graph. So in component 1, we have all the Banco, the string starting with Banco. And here a threshold is applied in the hierarchical clustering. And this is where the actual deduplication takes place. So basically, this is where the distinction is being made between the Banco Bilbao's and the Banco Santander's. At the bottom, in component 2, you see that everything falls below the threshold. So basically, all the Airbus strings belong to the same company, being Airbus. Let me show you on some data how this would work in practice. I share a demo that I prepared. I hope you can all see it. So we are going through all the steps of the DGU package on this data set that I prepared based on stocks 50 companies. So we start with a data table, just a row number and the name with the address included of those companies. The first thing is that DGU applies blocking rules, and the blocking rules that it found is basically one rule that combines 2, they call it predicates. The first one is the first token, so that's basically the first word of the string, and the second one is the first 5 characters of the string. And those blocking rules are applied to all the names and addresses. And then the combinations that end up in the same blocks are compared. So here we have the block data. Here we have the first block key, that is the first token. Then a colon, and then the second block key, that is the same 5 characters at start. And that is blocking rule 0. There's just one blocking rule here. And that is then calculated or assigned to each of the rows in the data set. Now let's have a look at some examples. In the stocks 50, there are a few companies that start with Deutsche. Those companies are Deutsche Post, Deutsche Börse, and Deutsche Bank. Deutsche Telekom, sorry. So here you see some examples of these companies. And yeah, because they all start with Deutsche, they all have the same first 5 characters, so they all end up in the same block. So for all the pairs that you can make, you only see 5 here, but there are many more. The string similarity metrics are calculated, so those 4 values, and the logistic regression probability that 2 strings belong to the same company is also calculated, and that's shown here in the score column. Then these probabilities so these names and probabilities end up in the probability graph, and that is the graph that you see here. And this is where I think the cool things happen. So here you see the edges show the probabilities from the logistic regression model. And here you see that the algorithm is correctly able to deduplicate the Deutsche Börse strings in one group. the Deutsche Telekom strings in one group, and the Deutsche Post strings in another group. And there are some interesting things to have a look at, because you see here that Deutsche Post, this one on the top left, and this Deutsche Börse, it has a probability of 0.7 that these are one company. So if you would just apply a threshold on probabilities, you would deduplicate them together. But because you apply this probability graph, and because you apply the hierarchical clustering on it, there's also the probability calculated between those two. And these are, this probability is much smaller. Moreover, the probability of this Deutsche Börse and this Deutsche Börse Frankfurt is very high. It's 100%, it's 1. So because this probability is so small, these two are also not combined. So it basically uses the information from all the graph, from all the connections between the representations of companies to decide on how to deduplicate. So I think this is a very, very interesting example. Another example, there are two companies in the Stoxx 50 that start with Bayer. One is the pharmaceutical, and the other one is better known as BMW, this one. If we look at the probability graph here, you see that this one, this pharmaceutical Bayer, has only a probability of 0.46 with the other one. But because they are so strongly linked to a third one, these two are also combined together. And there is no link at all with the BMW here. Does it always work? No, sometimes it doesn't. Let me show you an example of that. The two Dutch companies that start with Koninklijk, which means royal in Dutch. Let's give it a second. Yeah, here you see an example that it doesn't work. So this representation of Koninklijke Ahold is not matched with the other two because the probabilities are here just too small. I have to say that in this example, I didn't train it so thoroughly because I wanted to have such example in the demo. Let me go back to the presentation again. And then I explain you what we have done to make this work at scale. So let me summarize dedupe again. So we have the blocking rules that's first applied. Then within the blocking rule, within the blocks, we have string pairs. We apply the string similarity metrics. Then those 4 numbers enter into the logistic regression model. One single probability per pair is the output. That is in turn translated into a probability graph. We apply the connected components algorithm there. And in the end, in the hierarchical clustering of these connected components, of these components, the actual deduplication takes place. So in each of these steps, we basically took parts of the dedupe package and put that into Spark to make it work at extremely large scale, like millions of rows. In the blocking phase, we distribute blocking over all Spark executors. This operation is independent, so we could distribute that over the executors. And creating the pairs requires inner joining the result of the blocking table. So you see an example here, Airbus ends up in block Air. Let's say that you have a blocking rule of the first 3 characters. Then Airbnb also ends up in that block. This is not a Stoxx 50 company, but I needed a company starting with Air for the example. Then the Banco Santander, Banco Bilbao, they would also end up in the block BAN. You would create an inner join, and then you would end up with the pairs table that you see here. So for all these pairs, you would have to calculate the string similarity metrics and the scoring. So that's the next step. And this step, we again distribute over the executors in Spark. And to benefit here from parallelism, we increase the number of Spark partitions significantly. So we broadcast the string similarity metrics to the executors. We also broadcast the logistic regression model to the executors. and calculate it on all these executors and then collect it again. Something else that we did here, which is not part of the standard dedupe package, is that we remove the pairs that have a low score. If you look at the graph here on the right, or the bar chart, the majority of pairs is not a match. That is trivial. That's what you would expect. And the probabilities that are smaller than whatever 5%, there is really no chance that those pairs end up in a deduplicated entity. So we just throw these away. Then, we throw these away. Then in the next step, creating the graph, applying connected components, and apply the hierarchical clustering. This we do locally, so not on the executors. Dedupe uses the NumPy memmap, which is basically writing an array to disk to prevent memory issues. And to fill this memmap efficiently with data, so basically the data that's on all these executors in the Spark cluster, we reduce the number of partitions significantly before creating the memmap. This this results in shuffling in the Spark cluster, but because writing this memmap is time consuming, reducing the number of partitions before doing that is appear to be efficient. So in this way, we were basically able to use the dedupe package, which is created for local work, to the Spark executors and apply deduplication at scale for transactions in corresponding banking chains. I hope there are some questions.
Yes, thank you, Frit, for your presentation. We actually do have some questions in the chat, so let me start. Thomas asks, how efficient is the dedupe package? What was the maximal data set that you were able to process?
So let's start with the final question. The maximum data set is just all data that we had in scope for a particular project. This is in the order of magnitude of tens of millions of rows.
Okay, thank you. Then we have another question. Is this an interactive Streamlit app where we're looking at for the demonstration of the correlation between entities like Bayer and Koenig?
Yeah, it is. Yeah, short answer. It is.
Okay. Then, well, you have actually some compliments, very clear presentation. Thank you, very interesting. And also three other questions. First of all, did you look at human inference?
Human inference. I'm not sure if I really understand the question.
Or maybe it was still related to the previous one.
Yeah, so probably I should explain a bit more. So there is no training data set. So there is not a large data set that you manually label, throw into the package. So it's really this interactive labeling session. So you provide a large data set without any labels. And then the dedupe package, it organizes an interactive shell session where you have to respond yes or no to pairs, whether they are a match or not.
Okay, thank you. Then you have another question. What data set do you train on? Names on ING transactions that you know have a match?
No. Well, first of all, that's what I started with in the presentation, that this is explicitly for cases where these are not ING clients. Because if they were ING clients, we would know much more about them. You know, we would just be able to combine their transaction based on their account number. So this is we need to have explicitly not ING clients to apply this deduplication. And it's really interesting because these the representations are sometimes really messy. So sometimes there's really bad structure in the transaction details.
All right, and you have for now one last question. Simon says, thank you for sharing, Fritz. What process do you see to come up with blocking rules?
Yeah, so these blocking rules, this is part of the implementation of dedupe. And what they do in the package is they use a greedy set cover algorithm, this branch and bound algorithm, to come up with a set of blocking rules that leads to the minimum number of blocking rules that maximizes the answers that you gave to the questions during training, such that all the pairs that should belong together in the blocks are ending up in the same blocks.
All right, and then, well, actually, one last question. You are working only with unsupervised data sets? That was more like a statement.
That is a very broad question. No, of course not. No, because obviously, when it's about, well, first of all, when it's about telling the algorithm which pairs belong together, that is not unsupervised. And also when it comes to the step afterwards, where we create features and where we train a model to detect potential risk companies, no, there we need to label data, of course. Yeah.
All right. Well, that was actually the last question, and I would like to thank you, Fritz, for your presentation. So yeah, let's move on to our next speaker.
Thank you, Anna. Thank you, Fritz. And thank you, Stan, for the incredible presentation. And we go on for the third and last speaker of the afternoon. It's a very young data scientist. His name is Casper Ogeboon, and he joined the wholesale banking advanced analytic team at ING during his master from the University of Maastricht. And he loves crushing numbers and behind his computer, and also feels like his love for design and aesthetic through data visualization. And when he was a kid, he was always intrigued by mountains. So he always loved climbing mountains. And unfortunately, he just turned out as a data scientist, but he loves spending time off with his backpack on a higher altitude and hiking trails. So his presentation is about generating of synthetic financial times with GANs. And please, floor is yours, Casper.
Yeah, thank you for the introduction, Sam. My presentation will be on synthetic financial time series generation with GANs. I joined ING at the beginning of 2020 in February at Wholesale Banking Advanced Analytics team, and I teamed up with Fabian Janse and I did my master research there for Maastricht University, and I will go through the research that I've done at the university. So this really is a research project, and I'm excited to walk you through it. So let me first introduce what we have done, what the problem was. So I think some of you are familiar with generative adversarial networks, which is a machine learning algorithm that is able to generate synthetic images. Mostly, it is mostly used in image generation or video generation, and also known as deep fake images. And let me just give a quick example. We have these two images here, and I give you a sec to determine which image here is fake and which one is real. And it turns out that the right one was real, and the left one was just purely generated by a GAN network. And you could already see this by this slight distortion on the picture here left. So that was a slight catch there, but we will not go into detail why this happens. But what we will do is we will explore this generative adversarial network, not on the image or video domain, but extend it to the time series domain, and more specifically on the financial time series domain. So we came down to the following research question, which was, can GANs be trained to be a probabilistic model for financial time series predictions? And it is an important note here that we do not want to have a single perfect prediction for the future for a time series, but we want to have like a predictive probability distribution. So we want to plan out different kind of scenarios in the future. So let me first explain a bit more how a GAN network works. And this is an overview of a GAN network, where we basically have two different kind of networks, which are models, which are usually neural networks. So we have a generator and a discriminator. and each have a distinct task. So let me first introduce the discriminator. The objective of the discriminator is just basically a binary classification. So it wants to classify the incoming instances either as a real instance or as a fake instance. And the discriminator is asked to find the distinction between the data samples that are coming from the generator and that are coming from the real data set. And what the objective of the generator is contrary to the discriminator. The generator tries to fool the discriminator into thinking that its generated instances are actually real. So how can the generator learn this? So first, in training, we first give the discriminator a batch of real samples and a batch of generated samples with the labels 0 if it is coming from the generator and the labels 1 if it's coming from the real data. And in this case, the discriminator knows how to distinguish both the incoming data instances. And at the beginning, at the start, the generator has not learned anything. So it is initiated by random noise, so it just outputs random noise, and the distinction can be made quite easily by the discriminator. But then we update the generator weights by backpropagating the information that is stored in the discriminator to the generator. So basically, what the generator gets fed into is information that the discriminator knows whether this discriminator based its classification on. So the generator will become better and better at replicating real instances, and the discriminator has to improve itself further into making a better distinction between generated and real data samples. So in the end, this generator will be able, if trained correctly, to be able to output images or data instances that are similar to the real data where it was trained on. And if that happens, the discriminator cannot find a distinction anymore, and it will just randomly guess the label it is assigning to. So basically, the discriminator will end up as with an accuracy of 0.5. And this looks mathematically to the following loss functions. So we have a min-max game. So we have two, a maximize and a minimization on the loss function. So on the one hand, the discriminator tries to maximize the log probability of assigning the labels from real instances as label 1, and maximize log probability expected value of the instances coming from the generator as label 0. On the other hand, the generator tries to minimize the probability of generated samples assigning as label 1, and tries to maximize the probability of generated samples as classified as 1. So this is the basic GAN setup, and in our case, we wanted to deploy this on time series. So the first simple setup was on sinus functions, simple sinus functions. So the real data contained only one single sinus function, and the training process is explained here. So first you can see that it is just random noise, and it's starting to pick up the features of a sinus function, and in the end the generator is able to produce a sinus function, a neat sinus function. So this was still a simple setup. So now we make the data set a bit more complex, and we diversify the data set by varying the amplitude in the data set. So we still have a single sinus function, but we vary the amplitude. And these are some specifications on the training. But the output, as you can see here, is just one single sinus function. And this is a problem because the model is not able to pick up the whole distribution of the real data. It is only outputting a single instance from the data set, and we cannot force the model to increase its variety, because in this instance what it is producing is correct. It is present in the data set, but we cannot enforce the model to also create sinus functions with different amplitudes. And this is in literature known as mode collapse. which is a well-known subject in literature in GAN training. So we had to come up with a more advanced setup to be able to extract the underlying distribution of the data sets. So what we did is we came up with more advanced GAN setup, which is based on the Wasserstein distance. And the Wasserstein distance is a measure between probability distributions, and this is known as the Earth mover distance. So in this analogy, we have two piles of dirt, and we want to recreate one pile of dirt, but with minimum effort. So we want to have two exactly the same pile of dirt, but with minimum amount of effort into turning one pile of dirt into the other. And this is this optimal transport is called the Wasserstein distance. And in this picture, you can see here these boxes here. We want to move the boxes on the left to the distribution on the boxes on the right, and the optimal moving strategy with the least amount of work is indeed the Wasserstein distance between them. And this is the plan that was that's supposed to be optimal. So we move box in one box in position 1 to 0.7 and two boxes in position 1 to position 10. Still, the Wasserstein GAN need further advancements. So we created a gradient penalty, which was added to the loss function in order to make sure that the GAN is trained in a continuous space. And I will go into that a bit more deeper in the next slide. And we also added some conditional statements to the GAN. So what conditional statements were the previous time points from a time series. So we can give the GAN the last two or three time points, and then the GAN can predict the following time point from there on. So if we put this all together, we come to the following overview, which is still quite similar to the original GAN setup, but there are some distinct changes made. And one of them is that we do not have a discriminator anymore, but we use a critic. And the critic model here is trying to find a fitting function f. Function f tries to fit to the data coming from the real data set and fitting to the data samples that are coming from the generator. And when we present a batch of samples from the real data set, we apply the function to all these individual samples, and we get output scores for each sample. And we take the expected value from each sample, and this is an approximation of how the distribution of these samples look like. And we do that the same for the samples that are coming from the generator. So we feed in the batch of samples from the generator, and for each instance, we apply it to the function that the critic has learned, and the output scores. We approximate the distribution by taking the expected value of the output scores. And the objective here is to minimize the Wasserstein distance between the probability distribution coming from the generator and the probability distribution from the real data. And if we succeed, then these probability distributions will be equal. So then the Wasserstein GAN is able to find a fitting functions to the real data and to the generator and find the underlying distribution. And that's exactly what we want. We also added conditional statements. So we give the generator some information where it can be base its predictions on. So we concatenate to the random noise the last, let's say, n time points from the time series, and we feed it to the generator. So the loss function is as follows. As I explained here, this is basically the expected value from all the data samples coming in from the real data and the samples coming in from the generator. And we also add here the gradient penalty, and this enforces the function that the critic is learning to be in a continuous space. And this is pretty important to have stable training. So yeah, how can we validate whether the model was actually able to find the function and the distribution of a data set? So we came up with two synthetic data sets. The first one is a sinusoidal data set, which contains sinusoidal functions, different kind of functions with varying amplitudes, frequencies, and phases. And you can see a sample here. And we have an AR data set, which is a data set which contains functions from autoregressive model with two correlated variables. The following function here with the weights given, and we add a epsilon term to each point. So how does the model perform on this data if we present it to the model? The following results can be seen. So from visual inspection, we see here that the sinus functions have a great variety. So that's already improved compared to the last GAN model, where we can see here that the generator is able to make predictions and choose a certain frequency and a certain amplitude, and also stick with it. So, for example, if this generated red sample here, it has chosen to keep amplitude of 1.5, and you can see that that keeps it throughout the whole generation of the time series, which is pretty good sign. And also that we have a lot of variety in the generation now. And the same thing can be said on the samples generated on the AR model. So in red, we have the real samples, and in blue, we have the samples that are generated by the generator. And here we have the first 2 points are the conditions. So these are given to the generator. So the point here, this with point 2 is the first point that the model generates itself, and we can see that the path that it follows is similar to the real data, which is a good sign. But we want to investigate a bit further whether it also actually found the right distribution. So we can conclude here that it actually found the function, but also we want to validate whether the distribution, the underlying distribution of the data set was found. So let's evaluate this for the AR data set. These are all generated by the generator after it has been trained. So you can see here that if we condition the first point to be positive, the second point to be negative, if we follow the function where we created the real data set from, the next point must be negative. And this is one inspection that also holds here, so that the generative model is able to pick this feature up. And if we now take all these generated samples and we subtract the function from this, but we exclude the epsilon because we don't know which epsilon the generated sample has taken. So we end up with, for each time point, we have a bunch of epsilon terms, and we can make a distribution of all these samples and compare it with the epsilon terms that we set it to in the real data set. And that's what you can see here on the right. For each point, for this is 4.2, 4.3, we plotted samples of the epsilon term, and we have a high overlap in these distributions. So the real data set has an epsilon term of a normal distribution, variate, and the generated samples also follows the same distribution. So this gives a proof of concept that we were able to first find the function of the data set and also find the underlying distribution. So now this gives great confidence to model this on financial data set, where we do not have control over the function and we do not have control over the underlying distribution. So we need some kind of other metric to validate this. We chosen here to use the ING data on the euro-dollar forex exchange, which is a pretty fast data set where we sometimes have 4 data points per second. We took out a few days, and that should be enough for the training data. So I think this contains 1 week of training data of a price action. So 5 days, and the test set as well. And we deploy the Wasserstein GAN model on these financial time series, and this gives the following results. So we want to plan out different kind of scenarios. So we do not want to make a single perfect prediction. We want to see whether the model can give different kind of scenarios that could be valid in the future. So what you can see here in the plot is the first 3 points were conditioned. So these are the conditions given to the generator. And then the generator is free to predict whatever trajectory it wants. And this gives some kind of sense of how the probability distribution looks like. So we get a predictive cone with more of high density samples in the middle and less probable scenarios on the outer side of the cone. And this gives a pretty good view of that the generator is able to give really different kind of scenarios. The challenging task now is to find a way to validate this because we do not have the underlying function and distribution. So we came up with a p-value for p-value distribution, where we take for every time sample, we take the fraction of data samples generated greater than the real sample. And I will not go into the mathematical details, but there is a mathematical derivation that if you take the fractions of all the generated samples that are greater than the real sample, and these are from a continuous distribution, if you sample from that, then you would get a uniform distribution on the p-values. So that's what is shown here. So you can see here, these are the p-values on each time point, and if these are so for the higher time points, these are quite uniformly, so that's a good sign. And here you can also see that in the first point it is a bit biased towards generating samples towards the middle and not uniformly. So that was one way of validating this is still quite a general check to validate the model. So we wanted to take it one step further. So in this case, we wanted to predict time series that are longer than 30 length 30. So we want to increase the dimensionality of the model, and we have done so by introducing skip connections to the network. So we have these generator and the discriminator model, which are neural networks, and I will not go into detail how these skip connections work, but it gives the ability to a model to choose how many layers it actually wants to use. So for example, we give the model 15 skip connection layers. It can gradually build itself. So it will first use only 2 layers, and if it finds that it needs more complexity, it will add a 3rd layer. And so it can gradually build itself with the model itself. And this gave some pretty promising results, so that we could scale up the time series to 100 dimensions, and this could further be increased. So coming back to the research question, whether we could train a GAN to be a probabilistic model for financial time series, we have covered quite some interesting research, where we first found that the original GAN was not able to reproduce the data distribution of a simple sinus function data set. But we found a proof of concept on the Wasserstein GAN with the gradient penalty on the synthetic data set. So that gave us confidence to deploy it on financial data. and where we have shown that it is a strong performer as a probabilistic generator. And we also seen that these skip connections can be used to increase the dimensionality of the Wasserstein GAN. So that's also something that could be done in future work, more extensive research to these skip connections. And one other idea we had was to not only produce an ask price, but also produce a bid price. So we have a multi-dimensional time series generator. So we have two time series at the same time. And also what would be very helpful is if we would have a benchmark quantitative validation method for these time series, because this is something that is not present in literature. So this gives it's hard to compare models to one another. So that's something the research space could really benefit from. So yeah, that was my presentation. I hope you enjoyed it. If you have any questions, then I am happy to answer. And if you have any further questions or you would like to have an insight more on this topic, then you can find me on LinkedIn. Thank you.
Now, thank you, Casper. Your presentation about generic of synthetic financial time series with GANs has been incredible. And I see that you've been very lucky because Fabian Janssen has been responding quite to all the questions, but you're lucky because we still got a couple pending questions. So we've got Bouke Brennickmeijer, who wants to know about the GS divergence is the basis of the normal GANs loss. And the Wasserstein 1 distance shows more stable training and less model collapse in practice. So that is preferred.
Yes. Yeah.
Right?
Yeah.
Then the next question is from Ralph. And did you consider decomposing the time series and it might make it easier task? RNNS, for example, benefits significantly when predicting or decomposed series.
I'm not sure whether I understand the question, but the time series that we chose are we increase the variety of time series by a sliding window in the data set. So we don't, so we have a sliding window over the time series. So that's how we construct the data set. If that is what you intended to on the question, I'm not sure, but I will take a look at the question again.
Yeah, because it's from Ralph. Yes, he's asking another question, Ralph, again, decomposing into seasonal, trend, residual, or other decompositions.
Okay, yeah. So seasonal trends are not included, but that's something that the generator should pick up. But yeah, we all only trained on 5 days. So you could say something like, if we have training data for a couple of weeks, then you could see some seasonality in, for example, that Mondays open, there's a lot of price action. Or even if you take it further to a few months, then you could have the seasonality of different kind of the summer and in the winter. But this is something that is not included in this work now, because the train data was not that extensive yet.
I understand. We have 2 more questions from Hong Pei, and he wants to know about the validation of the model will depends on what you are going to do with the generated data. And
yes, so the generated data can be used, for example, in backtesting algorithmic trading strategies. So if you have an algorithmic trading strategy, you can train it on historic data, but it can easily overtrain on this single time series. So this GAN model, if it is validated properly, then you could use to diversify it on training these algorithmic training algorithms. And it could also be used to data sets that are difficult to share. So for example, if you have a time series regarding personal health, and one company wants to share with a different kind of company, then you could use these models to train on these time series and share the generated time series instead. But yeah, the validation is still a very interesting topic where more research needs to be done in how can we validate the exact, how can we validate whether the generated time series are actually correct. And there are still some, you could apply some statistical measures on this. But these, I applied a statistical measure on the returns, so the differences on the preceding points, and these statistics are shown that to be very similar, but still the whole time series you cannot really, you cannot compare statistically yet.
I understand. And again, a question from Hong Pei. He would like to know if you would like to train ML model with the synthetic data, for example, then you should compare the test results of model trained on the real and synthetic data and test it on the real data.
Yeah, that could be interesting to do as well. Yeah.
Okay.
Yeah.
I see that indeed Fabian had responded to all of your questions, and Ralph was also happy about your answer, and I don't see any more questions coming up. So I would say that if people would like to contact you or get more information from you, you've shared your LinkedIn profile, and also they can find you at the ING address shortly.
Yes.
So I want to thank you again for your incredible presentation. I want to thank all the other presenters, Mochabat and Boyang and Fritz and Stan. And I want to invite again Anna with me.
Yes. Hi, Sam.
Hey, Anna.
Thank you to all our presenters. As Samantha already mentioned, you guys gave really, really interesting and inspiring presentations indeed. And our audience was very happy, as I could also see. However, to close, I would like to give the word to Nicoletta, also from the WBA, who will talk about some useful links and blogs. So I would like to give the floor to her.
Hi, I hope you can hear me. Since this is our last meetup for 2020, I would like to take a few seconds and give a shout out to some people. Firstly, my colleague Samantha Buratini for her tireless contribution organizing all these series, and also my highly capable colleagues Jessie de Groot and Anna Calandra. And last but not least, our ING Tech community builder, Julian Grant, who constantly fosters collaboration and hosts a wealth of knowledge sharing meetups to his platforms. And now to get back to my presence here today, I'd like to share some interesting information about my team, Wholesale Banking Advanced Analytics, or WBA in brief. We are a multicultural, diverse team developing algorithmic data-driven products and are known for our quite unique culture, since we love experimentation and care about social good and diversity and inclusion initiatives. If you wish to learn more about us, you can check our Medium publications page, but also make sure to check our ING Tech Medium blog with top-notch content from our colleagues across ING. If you're interested in joining a great organization like ING, you can check our careers path. And for traineeships opportunities that can help you develop both personally and professionally, you can check the relevant page. We will make sure to share all this information with you at the after event email. And that's it from me. Thank you.
Well, then thank you, Nicoletta. We just then wish you a Merry Christmas, guys, and that's all for us. Our also last event.
Yes, but before wishing everyone happy holidays, we actually have to thank someone special, and this is Samantha here next to me. This is not only, as Samantha says, the last meetup of the year, but it is also her last meetup, unfortunately, because she will be leaving ING at the end of the month. So Samantha, on behalf of Jesse, Max, all the data scientists at ING, and myself, we would really like to thank you for your enthusiasm, your efforts, and your always present good vibes. So you always bring great energies and fun into our collaboration and into our work. And I'm really sure that your team and many other colleagues at ING all over the world actually are very happy with all your achievements. And we will really miss you a lot. So this goodbye is really on behalf of everyone. Sam, if you want to say something.
I cannot. Thank you, Anna. Super sweet. Thank you.
Yes, so thank you again. And so I will wrap it up. Thank you to all our speakers again for this amazing work, to all our colleagues, and we wish you happy holidays and a happy new year.
Bye.